Hello everyone, welcome to In 5 Minutes. In this video clip, we will discuss next special purpose digital filter which is called all pass filter. As the name suggests, it is a filter which will pass all the frequencies to the output side, and hence its magnitude spectrum will be flat or constant at all the frequencies because we do not want to block any of the frequencies. The question is then, why would someone use all pass filter when it is going to allow all the frequencies to pass? That is because magnitude spectrum is one aspect of filtering, which is obviously the most important one in most of the cases. But whenever filtering of signal takes place, apart from blocking of frequencies, the phase of each and every input frequency also changes on the output side. And hence phase spectrum is the second aspect of filtering. Now in some applications, I do not want to block any of the frequencies. I just want to change the phase values of input frequencies. Now in such a case, I can use all pass filter. It will not block any of the frequencies, but it will operate on input phases of the frequencies. I can obtain the desired phase of a particular frequency on the output side. So an all pass filter is defined as a system that has a constant magnitude response for all frequencies. That means if I write down mod h of omega, it will always be equal to 1 for all omega values from 0 to pi, and obviously from minus pi to 0 it will also remain 1 because of its even symmetry. The simplest example of an all pass filter is a pure delay system with system function. So for example, h of z is equal to z raised to minus k. This is an all pass filter. It's a system that provides delay. If k is equal to 1, it provides delay of 1 unit, z inverse, that can easily be made out from this block diagram. So suppose if I have a system with input x of n, output y of n, and the system function is z raised to minus k, output y of n will be nothing but x of n minus k. So if you want to delay any signal, you can use a delay block. If k is equal to 1, the input will be delayed by 1 unit. So such filter is an all pass filter. That is simply because if I find h of omega by putting z equal to e raised to j omega, this is what I get, e raised to minus j omega k. And if I now find magnitude of h of omega, mod e raised to minus j omega, we all know that magnitude of e raised to j theta, that theta can be anything, is always 1. So it becomes an all pass filter. However, we will look at more general case of an all pass filter. There is a trivial all pass system that has linear phase response characteristic. The system function of such an all pass filter in the most general form is given as h of z equal to an minus 1 z inverse plus dot 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 a1 z raised to minus n plus 1 plus z raised to minus n divided by 1 plus a1 z inverse plus dot 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 an minus 1 z raised to minus n plus 1 plus an z raised to minus n. So I've considered one system with this particular system function. Now if you observe carefully, in the numerator, the constant term is an. The next z inverse term has the coefficient an minus 1, an minus 2, an minus 3. As you go towards the higher order terms, the last coefficients are a1, and the z raised to minus n has coefficient equal to 1. Now the denominator also has similar terms. You can see z inverse, z raised to minus 2. The last terms will be z raised to minus n plus 1, z raised to minus n. But the coefficients are appearing in the reverse order. As you can see, the constant term is 1 this time, and that 1 is nothing but coefficient of z raised to minus n. Next coefficient is a1, so a1 comes from here. Then the last few coefficients are, you can see an minus 1 and then an at the end. So the only difference between numerator and denominator polynomials are that the coefficients are occurring in the reverse order. Otherwise, both have the same degree in both the cases. Now I can write h of z in compact form using summation. It will be summation ak into z raised to minus n plus k, where k will vary from 0 to capital N. and the denominator can be written as summation ak into z raised to minus k. K will again vary from 0 to n. Let me explain the denominator. Numerator can be explained in the same way. If I put k equal to 0, I get a0 into z raised to 0, which will be 1. So I get a0. So if I expand the denominator, I get a0 plus. If I put k equal to 1, I get a1 z raised to minus 1. If I put k equal to 2, I get a2 z raised to minus 2 plus dot dot dot. If I put k equal to n minus 1, I get an minus 1 z raised to minus n minus 1, which will be minus n plus 1. And if I put k equal to n, which is the last value, I get an z raised to minus n. So you can see I get the same denominator in this case. Just that we did not have a0 here, a0 was 1. So we will impose a condition saying that in this expression a0 is to be taken as 1. If we impose this condition, then I get the same denominator. Similarly, if you expand the numerator summation, you get the numerator polynomial which we had considered.